So we have a jetliner that lands and begins to slow down, and the mass of the jetliner is 3.5 times 10 to the power 5 kgs, and when it lands its speed is 75 meters per second, and the net braking force is 7.25 times 10 to the power 5 Newton. Now there are two parts in this question that we need to solve. In the A part, we need to find the speed after 10 seconds and how far it traveled in this time. So suppose this is the direction of motion, and its initial velocity for the jetliner we have 75.0 meters per second, and net braking force. So braking force will be opposing the direction of motion. Braking force would be in this direction. So if we take this direction to be positive x, so in vector form we can write that force is equals to 7.25 times 10 to the power 5 Newton with a negative sign and x cap unit vector. Now then we have to find the speed after 10 seconds. So first we will be calculating the acceleration, and to calculate the acceleration we can use the Newton's second law of motion. So acceleration, we have net force, which in this case is F divided by the mass of the object. So F we have minus 7.25 times 10 to the power 5 Newton, and the unit vector we have x cap, divided by the mass is 3.50 times 10 to the power 5 kgs. On solving, we get the acceleration to be equals to negative 2.07 meter per second square x cap. Now we can easily calculate the velocity, or basically the speed, after 10 seconds. Okay, for that we can use the kinematic equations. So v equals to v naught plus at. Now is equals to v naught, the initial speed we have 75, acceleration we have negative 2.07, and time we have to take to be 10 seconds. So from here the speed comes out to be as 54.3 meter per second. So this is the answer for the A part. Now next, in the B part, we need to find how far it traveled in this time. So delta x we have to find. So we can use the concept of average velocity here. So 1 over 2 v naught plus v, this is the average velocity. If you multiply it with time, that is delta t, you will get the distance. Other way around, you can use this equation also, x equals to x naught plus v naught t plus half a xt square. X naught is the initial position which we can take to be at origin. This goes to 0. Initial velocity we have, time we have, acceleration we have. We can put the values and we can find the value of x. Other way around, you can use this formula also. So for the time being, I'm using the first formula. So is equals to 1 over 2. V naught is 75. V is 54.3. Delta t 10 seconds. So from here, the distance traveled by the aircraft or the jetliner is 646 meters. So this will be the answer for the B part. So in this question, we are given that a drag racer crosses the finish line with a speed of 202 miles per hour and then deploys her drag chute. It's basically a parachute used for braking. Okay, so in the A part, we need to find what force must the drag chute exerts on 891 kg car to slow it to a speed of 45 miles per hour in a distance of 185 meters. So suppose there's a direction of motion, and this direction will be taking as positive x. Now its initial speed for the car when it finished the race, it is 202 miles per hour, and the final speed becomes 45 miles per hour, and the mass of the car is 891 kgs, and the distance traveled during the reduction of speed is 185 meters. So this is basically delta x is 185 meters. So to find the force exerted by the drag chute on the car, we will be first calculating the acceleration. And for acceleration, we can use the kinematic equations that we studied earlier. So we can use this equation, v square, the final speed is equals to the initial speed plus 2 times a times delta x. And from here, a is equals to v square minus v naught square divided by 2 delta x. Now we can put the values. The final speed becomes 45 miles per hour. So since this delta x given in meters, so we have to convert the units. So 45 miles per hour multiplied with 1600 to convert it into meters, divide by this is hours. Hour we can divide it by 3600 to convert it into seconds. So this becomes, the unit becomes in meters per second, and its whole square minus. Similarly here this would be 202 times 1600 meter divided by 3600 seconds and its whole square, and this whole divided with 2 times delta x. So delta x we have 185. Now you can solve it for A, and the value of acceleration comes out to be as negative 20.94 meter per second squared. So this is the acceleration. Now we can easily find the force. Now the drag force will be the in the opposite direction. In this direction will be the drag force F, right? So this is equals to mass times acceleration by Newton's second law of motion. So mass we have equals to 891 kgs. This is 891 kgs multiplied with the acceleration is negative 20.94 meter per second squared, and from here this force comes out to be as 18.7 times 10 to the power 3 Newton, and in vector form we can write the force to be equals to 18.7 kilonewton. We can write x cap and a negative sign. So this is the answer for the A part. Now in the B part we need to define the strategy that we use to solve part A. So first what we did, we find the acceleration by using this velocities and the distance, and then by using the acceleration and the mass we found the force or the drag force. Now one important assumption that we took to solve this question is that we assume the drag chute exerts the only force on the drag racer during breakup. No other force was applied. So this is the assumption that we took. So in this question we are given that a small car collides with a large truck that you can see in this figure. Now in the A part they are asking, is the acceleration experienced by the car is greater than, less than, or equals to the acceleration experienced by the truck? And in the B part we have to choose the best explanation given in these three options. Okay, so when the car collides with the large truck, it exerts a contact force on the truck, let it be F, and by the Newton's third law of motion the truck will also exert the same force but in opposite in direction on the car, so this is F. So the force is same on both the objects, but the acceleration will be different. Why? Because this car has a mass less as compared to this, and from the Newton's second law of motion we can write that acceleration is force over mass. So if mass is less, acceleration will be more. So for car the acceleration will be greater than the acceleration for the truck, so it should be greater. And options we can take, in the first part it says the truck exerts a large force on the car giving it the lighter acceleration. This is false, this cannot be true. Both vehicles experience the same magnitude of force. Yeah, that's true. Therefore the lightweight car experience the greater acceleration. This is absolutely correct. Third, it says the greater force exerted on the car gave it to a greater acceleration. No, the force is not greater, actually the force is same and opposite in direction. So only this second option is correct. So in this question we are given that we have a woodpecker that exerts a force of 230 Newton on a tree trunk to find the hidden insect to eat. Okay, and its effective mass of head is 0.025 kgs. We need to find the acceleration of its head away from the tree trunk. So basically we have to find the acceleration. Okay, from the Newton's third law of motion we know that the force exerted by the tree trunk on the woodpecker is equal in magnitude and opposite in direction to the force exerted by the woodpecker on the tree trunk. And by the Newton's second law of motion, the acceleration we have the force exerted on the body divided by the mass. Now we have to find the acceleration of its head away from the tree trunk. So the only force exerted by the tree trunk on the woodpecker is F, this F, which we have equals to 230 Newton, and mass for its head is 0.025, so we can put it here. This is 230 Newton divided by 0.025 kgs, which comes out to be as 9200 meters per second. This is huge. This acceleration is huge, which can also be written as 9.2 kilometer per second squared. So here we are given that an 85 kg parent and 24 kg child meet at the center of an ice rink, and they place their hand together and push. Okay, in the A part we need to find, is the force experienced by the child greater than, less than, or same as the force experienced by the parent. So for the A part we can use the Newton's third law of motion. The child exerts a force F on the parent, and by the Newton's third law of motion the parent also exerts the same force with equal in magnitude but opposite in direction, F. So forces will be same, so this will be, the answer will be same. Now in the B part we need to find whether the acceleration of the child greater than, less than, or same as the acceleration of the parent. So we can use the Newton's third law of motion here. So acceleration, we have the force exerted on the object divided by the mass. Now if you consider the free body diagram of the child, the only force acting is this F. So and mass for the child is less. So if mass is less, the acceleration for the child will be more. So acceleration for a child will be greater than the acceleration for the parent. Now next in the C part it says, if the acceleration of the child is 3.3 meters per second squared in magnitude, then we need to find the magnitude of parent's acceleration. Now from the Newton's third law of motion we know that the force exerted by the child on the parent is equals to the force exerted by the parent on the child with a negative sign because the direction is opposite. Now if you take the magnitude will be same. So what we can write, that the mass of child times the acceleration of child is equals to mass of parents times acceleration of parent, and from here the acceleration of parent is equals to mcac divided by mp. Now we can put the values. So mc we have 24, mp is 85, and AC we are given in the equation to be 3.3, and on solving we will get this value to be 0.93 meters per second square. And clearly we can see that the acceleration for the parent will be less as compared to the acceleration of the child. So in this question we are given that a force of magnitude 7.50 Newton pushes these three boxes, masses as shown in the image. Now we need to find the magnitude of contact force between the box 1 and 2 and the box 2 and 3. So for that, first what we can do is we can find the acceleration, and to find the acceleration of boxes we'll consider this whole three boxes as a single object. So the mass is m1 plus m2 plus m3, and by the Newton's second law of motion we can write that acceleration is net force divided by the mass. Now the only force acting is 7.50 Newton, and the mass we have m1 plus m2 plus m3. So m1 is 1.30, m2 is 3.20, and m3 is 4.90. Now from here the acceleration A comes out to be as 0.798 meter per second squared. Now we can find the contact force between the boxes 1 and 2. So I'll be making the free body diagram of this box 1. Now the only force is the contact force on the object 1 due to object 2, F12 we can write, and by the Newton's second law of motion we can write that this F12 is equals to, F12 is mass times the acceleration A, and this mass is m1 here. So m1 we have 1.30 multiplied with the acceleration we have found to be 0.798 1.798 meter per second squared, and from here this value comes out to be as 1.04 Newton. So this is the answer for the A part. Now in the B part, we need to find the contact force between the boxes 2 and 3. So for that we can make the free body diagram for the box 3. So this is our box 3. So M3 we have, and the direction of force is in this direction, this is F, and the contact force is in this direction, F32. Now the acceleration is in this direction, A. So from the Newton's second law of motion we can write that sigma F net is mass times the acceleration, and mass is M3 here. So F net we have F minus F32 is equals to M3 is 4.90, and the acceleration we have 0.798. Now from here we can easily find F32. So F32 is equals to F we have given in the equation to be 7.50. So 7.50 minus 4.90 multiplied with 0.798, and on solving we'll get F32 to be equals to 3.59 Newton. So this is the answer for the B part.